Hi, everyone. We're going to play a little game. It's my idea of a magic trick. And in the process, we're going to introduce some pieces to a hypothesis test, and we'll talk about the concept of p-values, which is a measure of how unusual your sample results are, under the assumption that the null hypothesis is true. Okay, so let's say I go around. This would be back in the pre-virus days. I go around the room and I ask people to pick cards off the top of a deck of cards. So I'm walking around with my deck of cards. I ask the first person to pick up the first card on the top. The first person picks up that card, shows the class the card, and it is a red card. I go to the second person and I ask that person, would you like to pick up a card? And that person says, why, I'd love to. So the person picks up a card and we see another red card. It could be a heart or a diamond. Let's say the third person picks up the card eagerly and we see another red card. I go to the fourth person. The fourth person picks up a card, another red card. What a coincidence. Fifth person picks up a card. It's another red card. Wow, what a coincidence, huh? Sixth person picks up a card, and it's another red card. And this has happened to me before, right? Just an amazing coincidence that the first 6 students to pick up the first 6 cards on the deck of cards, and they're all red. Well, what do you think? What assumptions might you have made if you didn't know I was a smart aleck? What assumption might you have made about the deck of cards? What do you actually see? And what are you now thinking? Well, now, you might be thinking, well, it could be chance, right? Maybe it was a coincidence. Or maybe you're saying, hey, I stacked the deck. Or I just brought out a brand new deck of cards. What, you accused me of stacking the deck? Yes, I did. In these little experiments of mine, it's a magic trick where I stack the deck. I realize that Penn and Gillette will not be very impressed with me. But yeah, that's my little magic trick. I've stacked the deck. Yes, I've stacked the deck. How did you know? How did you know? Well, example 1. We will look at the top 6 cards of a deck of cards, or the students did, right? What are the hypotheses? The null hypothesis and the alternative hypothesis. So the null hypothesis, H sub 0 or H naught, is that the cards are randomly ordered in the deck. See, if I were playing it purely fairly, right, fairly and competently, right, then I would have walked into class with a randomly ordered deck of cards where there was no rhyme or reason to it. It was a random deck of cards, right? And if you just see a random deck of cards on a table and it's not a brand new deck, then you might assume that the cards are randomly ordered. That would be your null hypothesis. And as we saw before in our probability unit, you can calculate things based on the assumption of a random order. The alternative hypothesis, H sub 1, is that the cards are not randomly ordered in the deck. So we live in a world where either the null is true or the alternative is true. Either the null is true or the alternative is true. But it's harder to base calculations on the alternative hypothesis because if I tell you that this deck of cards is not random, well, how would you base calculations on that? Right? What exactly is wrong, quote unquote, with this deck of cards? So it's much, much easier to base calculations on the null hypothesis because under this assumption, we can actually calculate probabilities. And we can see just how unusual this result is by chance. And the p-value will be a measure of that. So what do we observe from the sample data? I went around the room. The 6 students picked 6 red cards from the deck. We observe that the top 6 cards are all red. That was our sample data. The first 6 cards were all red. And then here's where the computation comes in. How unlikely are our sample results under the null, meaning under the assumption that the null hypothesis is true, under the assumption of a random deck of cards? Under the assumption of a random deck of cards. The null assumes a random deck of cards. How unlikely is it that the first 6 cards would be red? Well, what's the probability that the top 6 cards are all red under the null? It turns out to be 1.13%. I'll give you a few moments to try to remember how we did this. You may forget exactly how we did this, but you vaguely remember how we do this. I'll give you a hint. There are 52 cards in a standard deck of cards. We're not doing the jokers. I guess usually in an election year, I'd call the jokers the candidates, Trump and Biden. Okay, so we're not going to include the jokers. We have a deck of 52 cards. Half of them, 26, are red. And by the way, we're sampling without replacement. So that does make our calculations a bit harder. And 52 is not that big. So we cannot rely on like the polling assumption of independence. Do you remember how we calculated this? Well, what's the probability that if you really have a standard deck of cards, that the first card is red? What's the probability the first card is red? It's 1/2 or 26 out of 52, right? Hint, hint. So now, assuming that the first card is red, conditioned on that, what's the probability the second card is red? Do you see the pattern? Here we go. It's a review of probability theory. The probability that the top 6 cards are red, given that the null hypothesis is true, under the assumption that the deck of cards is in fact random. The probability that the first card is red is 1/2 or 26 out of 52. Given that the first card is red, we have 51 cards left in the deck, 25 red cards left. The probability the second card is red, given the first card is red, is 25 over 51. The probability the third card is red, given that the first 2 are red, well, 50 cards left, 24 reds left if the first 2 are red. So the third probability is 24 out of 50, and so forth. We count down the number of cards left in the deck. We count down the number of red cards left in the deck because we're assuming that we're always getting red cards these first 6 times. Work this all out, we get about 1.13%. And that's a measure of how unusual it is to get the first 6 cards being red if you have a random deck of cards, if the null were in fact true. So we can think of 0.0113 here as a p-value, a probability that describes how unusual the sample results are under the null. Kind of like before when we talked about confidence levels. How sure are you that mu is in the confidence interval? Here we're asking, how unusual is this? We're being a bit rude. How unusual is this? Our p-value, 0.0113, is a measure of how unusual this is if the null were true. A lower p-value means more unusual. So for example, if you had gotten 10 red cards in the first 10 cards picked, that would be even more unusual. That would have an even lower p-value. So what do we decide to do about the null? The null hypothesis said, remember, the null hypothesis said that the deck of cards is random. That's what the null hypothesis says. The null says the deck of cards is random. The lower the p-value is, the more unusual the sample results are under the null. So for example, here, there is a 1.13% chance that you would see that the first 6 cards were red. The null said the deck of cards was random. So what are you inclined to do with that assumption? Reject it or not reject it? The null says the deck of cards is random. Based on these results, are you inclined to reject the null or not reject the null? If you think this is low enough, and many people would, if you think this is low enough, you would reject the idea of a random deck of cards. The lower the p-value is, the more unusual the sample results are under the null, like the 6 red cards, or say 99 heads and 100 flips of a coin, if you assume fairness. And the more likely it is, we will reject the null and therefore accept the alternative. So here's something that Triola and others came up with. It's a nice mnemonic or memory device. If the p-value is low, the null must go, as in go away. Not go as in green light, not that. If the p-value is low, the null must go away. If the p-value is low, the null must go away. We're inclined to reject the null. So if the p-value, 0.0113, is too low for the null to survive, to hold up, so this is like overwhelming evidence against a person's claim of innocence, for example, then we reject the null. That is, we reject the assumption that the cards were randomly ordered in the deck. Later on, we'll refine the wording of this. So how low is too low? What is that threshold under which, if the p-value is too low, we reject the null? That threshold is called alpha. And we'll talk about this fish thingy in just a moment.